In this video, we're going to talk about implicit differentiation. So there are two ways to express y's dependency on x. One is as an explicit function. You can write y as an explicit function of x. So in other words, you've got something of the form y equals some function f of x. For instance, something like y equals x plus sine x. But you can also express the dependency of y on x implicitly. And that's where you've got an equation that is not solved for y. Something like x squared plus y squared equals 1. You recognize that probably as an equation for the unit circle. Now, that equation, this has y defined implicitly in terms of x. This equation has y defined implicitly in terms of x. You could solve this for y and get y equals plus or minus the square root of 1 minus x squared, and then you'd have y expressed explicitly in terms of x. But sometimes you have equations that are either difficult or really impossible to solve for y. If you had something like, say, sine of y plus y equals x, off the top of my head, I don't know how you'd solve that. So that you'd have y on one side by itself, and then on the other side of the equation you'd have only a function of x. So, what we're going to talk about is a way to find dy dx in the case where you've got y defined, or the dependency of y defined implicitly. You need to find, for that derivative, the reasons for using the derivative would be you needed a slope or a rate of change or something like that. So let's take a look at an example to show what's going on. In fact, let's use x squared plus y squared equals 1. Find dy dx for the equation x squared plus y squared equals 1. So what we're going to do is we're going to think of that y as a function of x. And in fact, I'm going to go ahead and replace y with f of x. So we've got x squared plus the square of f of x equals 1. Now what we're looking for in this case is f prime of x. And I want to do that without solving for f of x, because again, we're not always able to solve for f of x. So what I'm going to do is I'm going to differentiate each side. Since this side and this side are identically equal, their derivatives should also be equal. So let's look at the derivative. The derivative of x squared would be 2x. The derivative of the square of f of x, well, use the chain rule on that, or the general power rule, whatever you want to call it. We'll bring the 2 down. We'll have f of x to the first power, but then you've got to multiply by the derivative of what's inside. That's f prime of x. And then on the right side, the derivative of 1 with respect to x, that's 0. Alright, well now we can do some algebra and figure out what f prime of x is. So 2f of x, f prime of x, is equal to minus 2x. Divide each side by 2f of x, and we get f prime of x is equal to negative 2x over 2f of x. And if we like, we could rewrite that as dy over dx is equal to x, well, negative x over y. I'm canceling out the 2's, and I'm rewriting f prime of x as dy dx, and I'm rewriting f of x as y. So the derivative of y with respect to x is negative x over y. So if you wanted to find the slope of the unit circle at any point with coordinates x and y, you would just substitute that x and that y into the equation we've got here, and you can find the slope. Now, in some ways, that's not really as satisfying as you might like, because the derivative involves both x and y, but very often there's nothing else we can do about that. So let me show you how we're really going to do this. This is really the idea of the method of implicit differentiation, but it's not the notation that we use. Here's what we do. I'm going to rewrite this work, but instead of switching over to f of x, I'm going to leave everything. I'm going to leave all the y's in. So we've got x squared plus y squared equals 1. Now we differentiate each side of this equation with respect to x. So we're going to get 2x, and then here we're going to get 2, f of x is y, f prime of x is dy dx, and then we get 0. So notice that what we've got is this situation where we differentiated the function of x with respect to x, and that went just like it always goes. But when you differentiate a function of y with respect to x, because that's what we're doing, we're differentiating every term with respect to x. You differentiate this function of y, well, basically with respect to y, but then you have to multiply by a dy dx. Let's continue. We're trying to solve for dy dx. So we do what we did last time, subtract 2x from each side, 2y, dy dx is negative 2x, divide both sides by 2y, and we get negative x over y. So in summary, what you do is you differentiate each function, each term, or each side with respect to x, remembering to multiply by dy dx when you take the derivative of a function of y, and then solve for dy dx. So here's what you do. Here are the two steps summarized. You differentiate both sides of the equation with respect to x. Remember to include the factor of dy over dx when differentiating a function of y, and then solve the resultant equation for dy dx. So let's go back to our example and see if we can find the second derivative of y with respect to x. So find d squared y over dx squared. And again, the equation we're using is x squared plus y squared equals 1. Alright, so you know that to find the second derivative, you differentiate the first derivative. That's where we're going to start. dy over dx is equal to negative x over y. What we're going to do is differentiate each side with respect to x. So if you differentiate the first derivative, you're going to get the second derivative. Now what about this side? Well, we've got a quotient, let's use the quotient rule. So we have the we have the denominator times the derivative of the numerator. Well, the denominator is y. The derivative of the numerator is negative 1. Minus the numerator times the derivative of the denominator. And the derivative of the denominator is dy over dx. And then we'll have the denominator squared. So notice that when we differentiated a function of y, we included a factor of dy dx. When we differentiated a function of x, we did not include dy dx. So here, when we had the denominator times the derivative of the numerator, we were differentiating negative x, a function of x. There was no need for dy dx. The derivative of negative x is what it's always been. But then after the minus sign, we have the numerator, negative x, times the derivative of the denominator. Well, that will be 1, and then multiplied by dy dx. We were differentiating a function of y there. Alright, so this turns out to be, I'm going to rearrange this. This is going to be a plus x and a minus y, so I'm going to write this as x dy dx minus y over y squared. Now, we're not finished. We really need to replace dy dx with the formula we found for dy dx. Remember that we found the first derivative to be negative x over y. So I'm going to come back over here. D squared y over dx squared is equal to x. I'm going to replace the dy over dx with negative x over y. We've got minus y over y squared. So that's the same thing as negative x squared over y minus y over y squared. Now I want to simplify that some more. We've got a complex fraction, and that we've got a fraction containing a fraction in its numerator. So let's multiply the numerator. Let's multiply the numerator by y, or y over 1, and then let's multiply the denominator by y. So we're really multiplying by y over y, which is 1. Alright, if we multiply this by y over 1, we're going to get negative x squared, the y's are going to cancel out, minus y squared over y cubed. But wait, there's more. If you factor out a negative 1 here, you get x squared plus y squared. And remember that we started with x squared plus y squared equals 1, so let's replace that x squared plus y squared with 1. And we get negative 1 over y cubed.